Good evening. Anjali, can you hear me? Am I audible? Hello, hello, hello. Can you hear me? Hello, 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 hello. Uh, Please respond if you can hear me or if you can't hear me, please. No.
Hello, sir.
Yeah, yeah. Anjali, can you hear me?
Um, your voice is not clear, sir.
Oh, is it not clear? Uh, just a minute. Hello.
Yes, sir. Now it is fine.
Now it's fine. Or is it not clear? Should I change something or is it fine?
It is fine, sir.
Okay, okay. Anjali, are you attending all the sessions? All the problem
Yes,
solving
sir.
sessions?
I'm attending all the doubt sessions.
Now, you registered for the exam?
Yes, I have registered for the exam.
Okay. What do you do?
Sir, I'm PhD scholar and in my research work I need MATLAB programming, so I'm on this platform.
Okay, okay. Where are you doing your PhD?
Sir, from HBTU Kanpur.
Okay. Is it helping you? Is this is this course and also this sessions, problem solving sessions?
Yes, sir. It is helpful for the
Uh,
assignments and my work also.
so, are you expecting anything else from this, like problem solving sessions? Course will go on as it is. Uh, do you want anything else in these problem solving sessions, or like is it
For right now,
enough
for this current session, I have a doubt for with one assignment question.
with assignment session? Okay, I'll just share this. Uh, yeah, it's- okay. Which one is that?
Sir, the second one.
The second one. Okay,
So it is saying that download the file and use the function.
okay, okay. So, are you not able to download it? Uh,
Yes, I'm not
is
able
that
to download it the way.
okay? Is not you couldn't open this?
Yes, sir.
Ah, it's no problem. You can write this. You can write this function also. It's not. Yeah. Or you can take a screenshot of this
Okay,
if
sir.
you are not able to download. Or I can do a thing and copy and paste in the chat box.
Okay, sir. Thank you, sir.
I was asking like if you want anything else from these sessions, like are these sessions helping you or like are you expecting something else? Uh,
For this session, I am not expecting anything because I was just trying to solve these questions from the code.
okay, okay. No, I'm just asking like in general.
No, sir, not like that.
Okay. Yeah. Okay, so we'll just revise first what has been discussed in this week, and then we'll probably look into those this practice assignment questions if time permits. So this week we have gone through numerical differentiation and also numerical integration. I think last week, what did we go? Last week we had gone through this solving nonlinear equations, like this Newton-Raphson and all these methods, uh, fixed point iteration and whatever all those methods we have gone through. So this week we are entering into a new area, which is solving the differential. Sorry, not solving differential equations, but like getting differentiation of functions using numerical techniques. So whatever we have learned, maybe in our plus two graduation, not in maybe might be in plus one, plus two. If we might like we might have heard like learned doing differentiation and integration in an analytical way. So like we first learn about functions, then we learn about limits, and then we go to differentiability, continuity, all those things, and then we go to this new analytical differentiation and then integration. So here we are trying to do the differentiation by some numerical techniques. So sometimes it will like doing analytical differentiation may be very costly, or sometimes it might not be possible. Differentiation you might do maybe, but like integration is like a very difficult thing. Like for certain integrals, getting integrals like analytically is not possible. So then we have to go through the analytical, sorry, the numerical route. So in the first lecture of this module, we have seen differentiation in single variable. So in single variable differentiation, we have seen the forward difference formula, central difference formula, and the backward difference formula. So this numerical differentiation formula of the forward, this is the forward difference formula. So this we get through by using this Taylor series. So we have seen I think in the first module or second module Taylor series. So this we truncate till the first order, and then we uh, subtract minus f of x on both sides, and then divide by h on both sides. We'll get the forward difference formula. So this is the actual differentiation limit h tends to 0. This is the actual analytical differentiation which we do. This is the numerical integration. So because we are truncating here like a lot of things, so like we can see like all these things we are truncating here, like h square, h cube, uh, all these things in the Taylor series we are truncating. So that's why here the order of uh, truncation is for the order of error is uh, h. So if you like reduce the value of h, the step size by h, then the error will also reduce by a factor of h. So similarly, if you want to get the backward difference formula, you just take the Taylor series expansion of f of x minus h. Then you do the same thing, truncate it to first order, and then you can do subtraction and the division, and you'll get the backward difference. So same here also, the order of error is h. And here, if I want to get the central difference formula, which is a very good, uh, which will give like very good approximation, and you can see the order of error is also like h square. So that's why it gives a more more near more near to the accurate value compared to these two forward difference and backward difference. So central difference formula we just get by taking the Taylor series of f of x plus h, and then we take the Taylor series of f of x minus h, and then we subtract. We only take the first order terms, and then we subtract both the Taylor series, and then you will get this uh, Taylor series expansion, series central difference. So these are very simple uh, techniques which we can use to do the numerical integration. This is for uh, single variable. So this we have seen like this is the example which we saw in MATLAB. We have coded this in the class. Uh, is that first? Yeah. So simple simple thing like we are doing the numerical integrations. Sorry, numerical differentiation of tan inverse x. So we know the analytical differentiation formula of tan inverse of x, which is 1 by 1 plus x square. So that's why we'll just, so we have to differentiate this, we have to find out the value of derivative of f of x at x is equals to 1. So we'll assume like this is the point of integration u is equals to 1, and then this is the true value which we get by 1 by 1 plus x square, or here I am taking the variable name as a. So that's why it is 1 plus x. And here I'll try to find out this value of differentiation for different step sizes. So this ranges from 10 to the power of minus 1 to 10 to the power of minus 5. So 10 to the power of minus 1, 10 to the power of minus 2, 10 to the power of minus 3, 10 to the power of. So for these step sizes, I'll try to find out the uh, differentiation, value of differentiation of f of x at x equals to 1, using the forward difference, central difference, and also the backward difference formula. So this we all like this is uh, f of x f of x plus h, and then f of x, and then we have this uh, differentiation. Uh, Sorry, division by h. So here we are using dot h dot slash h because we are taking a vector of subsizes. So we want to uh, do element wise division. So that's why we are doing. So A tan inverse, this is A tan A plus H. A means here, this is the tan inverse of A plus H. So this is the uh, uh, function which we use for tan inverse in MATLAB. So sine inverse, if you want to do sine inverse also, you use A sine something like that. So, and we are also having the error. So we are also calculating the error, which is the true value. This is the true value, and this is the numerically calculated differentiation value using the forward difference formula. So, and then we also do the same for central difference and backward difference. Like we have seen the formula accordingly with code and the rest. Then then after that we plot the errors versus the step size. So, and let's see how it will look. We are if we plot this, so these are the errors, and where is the So this is the plot. So now you can see here, this is the central difference formula, the plot using the central difference formula. You can already see that the error is much lesser in central difference formula compared to the forward difference and the backward difference. The error is less. So error is on y-axis. So this red dashed line lies below this solid blue line and solid uh, this uh, magenta color, dotted, dotted and dashed. So already the error is less, and also you can see the slope of this line is steeper. So as I go from 10 to the power of minus 1 to 10 to the power of minus 2, as I reduce the step size from 10 to the power of minus 10 to 10 to the power of minus 1 to 10 to the power of minus 2, my error also reduces by a factor of uh, 100. So this is why the line is like steeper than what we are getting in forward difference mode and center difference. So this shows how uh, error is like varying with respect to step size in the forward difference, backward difference, and the central difference mode. And the errors are also given here in the central difference. We can also get these errors for the backward and forward. Let's say if I further I want to uh, go from 10 to 10 to the power of minus 1 to 10 to the power of minus 10. Like I want to reduce step size much further. So if I do that, if I run this again, I can see that I'll reduce the step size. The error is also reducing with reduction in the step size. And after some certain point, the error is increasing in the central difference and also in the forward and the backward difference. This happens because we have seen this truncation round of errors. Truncation is also already we are doing in the Taylor series. And then we are having the round of which happens to the machine precision because MATLAB has a precision value, which is nothing but like a least count of MATLAB. So if we go beyond a certain value, error will again start increase. So this is the thing which we have seen uh, in the central difference method. These are the things which we have seen, like forward difference, backward difference, and central difference for this tan inverse of x. And then we have gone to this uh, next module. This problem also we'll see if we can do it. Just we have to change the function, nothing else. We do it, we'll get the same thing. And then we have gone to the next lecture. Is also central differentiation in single variable. But here we have to uh, do the second derivative. So second derivative using the central difference scheme, and also the third derivative is also there. So third derivative, we'll see how we can get the second derivative. So this formula also it's not a very difficult thing to get. We have to, as I have said, we have to uh, get the Taylor series expansion of f of x plus h. Instead of truncating till first order, we'll truncating we'll truncate this Taylor series till the second order. So I'll keep all these terms, and I'll again also define the Taylor series for f of x minus h. And again, after that, I'll subtract f of x plus h and f of x minus h, and then uh, again doing some addition and subtraction on both sides, I'll get this formula. So it's not like a different, something totally different. So this also is also this second derivative central difference formula is also derived from the central this Taylor series only. So this I think we have given Last some problem. Okay. Okay. I think we don't have the second order difference something, but yeah. Let's say this is only the problem. If I want to do central difference, uh, uh, central difference for this only, I can add here only like, using this formula. So f of x plus h is already there. F of x minus h is already there. So I have to add this additional term, which is minus 2 into f of x. So here, if I add this minus 2 into here, we have to do it here. So instead of central difference, I'll write this as second order central difference. So an additional term I have to add, which is 2 into a tan here on this. And here I have to get h square. Right. Yeah. And this is also plus. So everything else remains same. If I do it, I'll get the second order differentiation. So say if I just plot it, this thing is missing. Okay. This I have to do. This error is also not perfect. I'll just run it till here. See what it will do. Yeah. So this is the second order differentiation. Like we can see, uh, this is the value for different step sizes, and here it is reducing, and then it is like increasing, and then it's like reducing. So weird behavior. So like this, we can do differentiation for a single uh, single variable numerical differentiation. So then we have also seen this example of the Arrhenius reaction, I guess. So this was the one. So all the values are given, and this we have to use uh, this here T is the temperature, which is a variable here. We have to differentiate. with respect to this reaction rate with respect to temperature, and we have to get the value of R dash using the central difference modeling. So this is the code for that, and we are also using like in the same way we are like using the different step sizes here, and we are defining R1, which is f of x plus h, and also R2 is nothing but f of x plus f of x minus h. So nothing but like here 2t you have to add plus h, and minus t you have to do. And then we have the same thing like central difference model. This is the first order differentiation model. F of x plus h minus f of x minus h by 2t. So to do that and we plot it, we have to close. So this plot was overlapping. So we also have to add close all. So we don't do it. Again, plots will get overlapped. We are not plotting anything. So just we'll see, we are just seeing the errors here. So these are the values of numerical differentiation for different step sizes, and these are the values of error. You can see that error is reducing, and then after that here the error becomes zero, and then again it is increasing. So this the third value of h, which is like 10 to the power of minus 5, is our uh, uh, the minimum like value of h which we can use. After that, if I reduce it further, again the error. So there is no point of uh, uh, decreasing the step size, because the uh, round of error will accumulate, and again the error will. So this is the first order differentiation. All the different things which we have seen in first order differentiation. And then uh, we have gone to the partial derivatives. So the same problem which we had done. So here we are we have this like we have solved these two problems here. One is this we have okay, we have solved this. This is the function of x1 and x2, and we have to differentiate with respect to x1 and x2. So when we do partial differentiation, we know that we have to keep the like when I do a particular partial differentiation with respect to a particular constant, I have to take all the other uh, variables as constant. Here I am differentiating with respect to x1, so x2 should be taken as constant. Here I am differentiating with respect to x2, so x1 should be taken as constant. So then if I want to give the partial differentiation with uh, respect to this, I can use the central difference or forward difference. Whatever I want, I can do, and I can get the partial differentiation of f f with respect to x1, and partial differentiation of x with respect to x2. So whatever I want, I can. So this is also another problem in which we have seen that the same problem for the Arrhenius reaction, rate of Arrhenius reaction. Here, I want like uh, two variables. So here we are taking C as also variable. C is the concentration, and T is also temperature, which we have already seen, is also the variable. So if I want to get like this partial differentiation with respect to E and C, we can code like we can use the central difference or whatever power difference we can do. So this is uh, uh, the partial differentiation for this Arrhenius reaction, rate of Arrhenius reaction. So this is the formula which we got, and C is given and also T is given. So here I am first I have to differentiate with respect to T, right? So here you can see that like when I say x1 here, x1 has the variables T and C. Both the variables T and C should be there. So T, I have to like if I want to do the partial differentiation, I should have f of x1 plus h comma f x2 minus f of x2 minus f of x1 minus h minus comma x2 by h h1. So 2h1. So this is the formula you can see. This is the uh, partial differentiation of x with respect to t. And similarly, I can, if I want partial differentiation with respect to c, I have to take these increments in c, which is nothing but f of x1 comma x2 plus h minus f of x1 comma x2 minus h divided by 50. So this is the formula. So if I use this and do that, like I will get the partial differentiation of r with respect to c and r with partial differentiation of r with respect to c. So I'll make sure I'll add ELC and also clear so that all the previous variables are cleared in the workspace and also see. So these are the partial differentiation values of this t and with respect to r with respect to t and also partial differentiation of r with respect to c. So in the lecture, this module, I think third lecture, I guess, right? So in the third lecture, there was a slight error that professor missed this multiplication with two. So here I have corrected. Like if you have gone through the lecture, I think the answer there was something 30, 98 point something 6, 38.6 something. So there was slight error. You can rectify it like if you have taken the same one. So that's how we do partial differential uh, respect to x. This is the same thing for this function, which is sine x1 into e power x minus 2. So we are defining the function here, and then we will call the function and get the values. So here we are taking same step sizes, one e power one e minus 6, which is 10 to the power of minus 6 into the power of minus 6, and the values at which I want the point differentiation is uh, x1 is equals to zero point 0.5 and x2 is equals to 1. So these are the values at which I want the partial differentiation uh, of f of x with respect to x1 and x2. So then I can get this is the true value. So true value can be derived like because we know we can do the analytical integration, we know the true value. So this is the formula. This is dou by dou f by dou x1. This is dou f by dou x1. And then I can do the uh, same thing. Like I have to get differentiate with respect to x. So here x is a vector here. So you can see x is a vector which has which I'm getting, which is storing the values of a, which is 0.5 and 1. Then I am incrementing the x1 value because I want to do differentiation with respect to x. So I want like I'll add h to x1 and then I'll also subtract h with respect to x1 so that I can get f of x1 plus h and f of x1 minus h. And then after getting this value, I'll do this using the central difference formula. Similarly, if I want this, I am doing it here. The same thing which here we are doing instead of like uh, doing all this things. Similarly, like I think like we can call the function and also do like we have defined my function tree. We have we are directly doing that. So same thing like this is I can take this as x2. Uh, yeah, okay, fine. It's like I'm defining a vector of h and I'm adding only the value of this. So temp h of 2, which is nothing but I'll add h of 2 here to my x2 value. X2 value is a2 here. So, and then I'll do the numerical differentiation to get the differentiation of x with respect to x. So do by x. So if I calculate the errors and do this thing and use and add CUC here. So this is the numerical derivative of f with respect to x1 and this is the numerical derivative with respect to x2 and these are the errors. So that's how we can do the partial differential equation. So the partial differentiation. When will we do partial differentiation? When we have more than one independent variable. So we can see that we have two independent, which is x1 and x2. So that's how we can go about doing partial differentiation. This was the differentiation which we have learned in this module, and then we have gone to the integration. So numerical integration. So numerical integration is also a very simple thing. So integration is nothing but the area under the curve. Like so if you want to integrate a function f of x from a, like x is equals to like from a to b, then you have like then we are what we are doing is we are trying to find out the area under this curve f of x from a to b. So, so this I can do by using the uh, numerical techniques. As I've said, like sometimes numerically getting the integral values is very difficult. Like you might like there are a lot of functions where there is for which we don't have numerical like analytical integration cannot be done. It's like very impossible to. So in all those cases, and also if you want like faster calculations, you can use this numerical integration. So there are different numerical integration techniques. So all this can be uh, come under like this numeric Newton codes integration formula. Like if you want to learn more about these things, like you can go to this computational techniques course, like more detailed explanations are given. But like all these techniques come under the Newton codes, like uh, generalized form of all these techniques is the Newton codes formula. So first, the simplest is the trapezoidal rule. So in this, what we'll do is like we'll take the value of f of x at a, which is f of a, and we'll take the value of f of x at b, which is f of b, and we'll join these 2 points by a straight line. We'll because this is a trapezoid, so I can use the formula of area of trapezoid, which is a plus b by 2 into h. So here a is this f of a plus f of b by 2 into h is this. H is nothing but b minus a. So that is the trapezoid form. Let's say if I want to take 3 points instead of 2 points, if I want to take 3 points. So when we have 2 points, remember that like when we have 2 points, uh, uh, we can exactly fit the uh, single degree curve for 2 points, which is the straight line. So I have 2 points. I can exactly fit this like without any errors. I can exactly fit this uh, single degree curve, which is a straight line. Like if I want to fit a parabola here, like I can fit multiple parabolas. But if I want to fit a straight line, like a single, if I want a single solution joining these 2 points, which uh, which para which polynomial can be used is like a straight line is the perfect thing to join two points. Like if I have 3 points, then the perfect thing which can be joining them is a parabola. So which is nothing but a second degree polynomial. So if I have a three, if I have like instead of three, if I have four, then we can use the fourth order uh, polynomial. So like that, if I keep on increasing, uh, if I keep on increasing the number of points which I take to evaluate the integration, this thing will the value of the integration which uh, numerical value of the integration which I calculate will become more accurate. So when does the accuracy, like if I have some, like let's say some, if I want to find out numerical integration of let's say sin x, then probably if I increase the number of points, like if I go from trapezoidal rule to Simpson's one-third rule, my error will reduce. If I go from say, Simpson one-third rule to Simpson's three-eighth rule, my error will reduce further. So the value of numerical integration will be much more closer to the true value. But if I have, let's say, only a straight line, like f of x is only a straight line, then there is no point I have, like, then there is no point of using the Simpson's one-third rule and Simpson's three-eighth, because like that will give uh, some like again increases the complexity, and also sometimes it might give you an error. So depending upon the curve which you have, like you have to use. So most of the times what we do is we take either Simpson's one-third rule or trapezoidal rule, and we'll do it for a lot of intervals. So I think in the next lecture we have discussed like multi-step trapezoidal formula we have discussed. Like we'll divide this entire domain into small steps, and we'll do the trapezoidal rule for this small part, and then this part, then this part, then this part, and we'll add all this. So that's what we do. So this is the trapezoidal formula. Like as I have said, this is nothing but f of a plus f of x plus h by 2 into h. So h is nothing but b minus a. So area of the trapezoid. Then we have the Simpson's one-third rule. This also can be derived, like if you want, you can watch the computational examples. And then we have the Simpson's 3/8 rule, similar. So s- we can use this to find out the numerical integration of a curve from like in between 2 points. So the order of error here is like third order. Local truncation error is third order. And in Simpson's one-third rule, it is like as I said, it further decreases to fifth order, and 3/8 rule also it is of like error decreases by a factor of 5. Like uh, if I if I have h reduced by a factor of 10, then my error will reduce by a factor of 10 to 1. So that's what this using the different methods like trapezoid one third, and Simpson's eighth third, Simpson's 3/8 rule will get us the numerical differentiation, but with different errors. So this is the uh, uh, problem which we are solving here. So which is 2 minus x plus log x using the different techniques, Newton codes formula. So what are the Newton codes formula which we are using? First one is that trapezoidal rule, and Simpson's one third rule. Three two things which we are seeing here. So this is the lower limit of integration. So x is equals to 1 and x is equals to 2. So in between these 2 points, we have to find out the area under the curve f of x, which is 2 minus x plus log x. So this is the true value. So this is the integration of this. Like if you do the integration, you will get this. Is x minus x square by 2 plus b into log x. So all this. So this is the integration. Like if you, this is the different definite integration, not the indefinite. if you do it, like analytically, if you do it, you will get this true value. So we don't want, like we want to now go, like the objective is to learn the numerical differentiation. Right? So here, this is the trapezoidal rule. I am saying single differentiation because we are only taking one step between the points A and B, which is h is equals to b minus c. So I'm not dividing it into further steps. So a single application of trapezoidal rule. So I'll take the value of f of a. F of a is nothing but, so I have already defined a function f, my function integration, uh, my function int x. So I give the value of x, this will give me a value of function, evaluated value of this. So that's what we are doing. So we are getting the value of f of a and f of b, and we are using the trapezoidal formula, and we are also getting the error here. And we are also like, now we also want to use the Simpson's one third rule. In Simpson's one third rule, we have 3 points, right? So the step size will reduce by half. So like there will be two intervals between 3 points. So that's why here h is b minus a1. Right? So the formula is the same thing, h by 3 into f of a plus 4 into f of x plus h, uh, into f of a plus 2h. So this is the Simpson's one third formula. And then we are also getting the true, we have the true value and we are getting the error. So if we do it, we'll get whatever the calculation this does. So you can see that in the trapezoidal rule, this is a error, 0.039721. In the Simpsons rule, you can see that this error has reduced, like uh, like much more, like it has reduced by a lot. So compared to the trapezoidal rule, we can say that Simpson's rule is much more this much more near to the true value, much more accurate. So these are the values of approximation, 0.84 and 0.88. And what is the true value? So uh, true value, um, true value is 0.8863. So both these values are very near. So I cannot say like they are like uh, exact as the true value, but these are, as I've said, like numerical techniques will give you a closest answer. Like it will give you an approximate answer. It will not give you an exact answer. Sometimes it might give, depending upon the step size which you take, all these things like matter. So if I take multiple step sizes here, maybe I can get a uh, much more, much more accurate value of trapezoidal rulers. So numerical integrations will give us a value with which we can get satisfied, because numerical techniques will reduce us a lot of time to do the calculations. So that's why we lot of times, like we when we run simulations, like this is a very simple thing. Like it is like MATLAB is doing it like just like that in a fraction of a second. But if you want like you want to run some simulation which has like complex differentiations and complex integrations, it will sometime like take hours to solve the entire simulation. So if I want to reduce my time further, I have to resort to numerical techniques a lot of the times. And due to that, from my like, let's say if your simulation is taking 1 hour, you can reduce it like depending upon the number of integrations or differentiations you can reduce your time of simulation like 1 hour simulation. Maybe you can run in 20 minutes or 15 minutes because you are using the numerical techniques. And also these are like very stable compared to the other things. So that is the advantage which we are getting. So that's what this course should teach us, like how to use these numerical techniques to do the differentiation and also integration. And also, we are also going to see how can we get the in the next module, I think, how can we get the solution of differentiation, sorry, solution of differential equations. So these numerical techniques are very helpful. So, but we have to be careful, we have to be very careful with the step size. Like, otherwise, like if you take a very high step size, like your error will be also high. Because here I can get the true value easily. Like this is a very simple function. I can integrate it from A to B analytically, and I can get a simple, like simply I can like this is a very simple integration. Directly I can do, but a lot of times I cannot get this true value. So here you can tell that this is the error, but a lot of the times you cannot tell it. So we have to be very careful while giving the step size. So we have like we make sure that step size is as small as possible. Like I cannot take my step size very low also. Like depending upon the problems, your step size will vary. How will you decide the step size? That will depend upon the problem which you are solving and your domain expertise. Like if you are a mechanical engineer, you know that like how much step size you can take. Like let's say if you are differentiating or integrating with respect to time, you know that like you can take step size of 1 second or 0.1 second depending upon the problem which you have. So that compromise you have to make somehow, and your calculations will depend upon that. So so always we'll get approximate values which are which have to be near to the true value. So this we have seen the trapezoidal rule, and then we have gone to see the numerical integration uh, for multi-step trapezoid and for like multi-step Simpsons rule. So here, as we have said, instead of like taking a step size of h, what we will do is we'll divide this interval between a and b into a lot number of uh, like n number of regions. So 1, 2, 3, 4, 5. Like I can divide it into further n intervals. So interval between a and b. And after that, what we do is we'll take trapezoidal rule and get the numerical integration of this region and this region and this region and this region and this region. And I'll sum all this numerical integration values for all the regions, and that will give me the value of this integration from A to B. That is the multiple applications of trapezoidal rule which you are talking about. This will give me reduced error compared to like if I have a straight line, like if I had simply taken a straight line and I joined these two points, now you can see that this whole portion I am not calculating. Like this is the amount of error which I have to face if I use a single step in trapezoidal rule. Yeah. So if I use this like a lot of steps, now you can see that if I join a straight line from here to here, here to here, to here, my error is getting reduced a lot. So that's why you use multiplication. Like we can divide our domain into domain. When I say domain here, it is nothing but A to B into further more number of intervals. So like if you divide it into much like many like a smaller like let's say from some thousand or like as you keep on increasing the value of n, your error will reduce much more, even much more. So if this h like the value of h, which is nothing but a to a plus h, if this like comes near to zero, then you are like basically getting the value of exact integration using this trapezoid rule also. So limit h tends to zero, then you'll get like very close to the true value. So that's what we can do. So this also we have coded in the uh, this was coded in the class on numerical integration multi-step. Yeah. So So this is like uh, we are we have this we our domain is divided into n intervals where interval each interval has a step size of h. So h is earlier h was b minus a, and now we are dividing into n intervals. So that's why I'll divide this h by n, and I have my domain from a to b, which is divided into a lot of integrals. So a plus h, a plus 2h, till a plus nh, which is nothing but b. So this is my x vector, and I have to find out the values of f vector using my uh, function which we have defined already. So if I give this vector as the input, I'll get function evaluations of my function at all these points a plus h to b. So now we can like get the integration. What we can do is like for getting the numerical integration using the trapezoidal rule, for each interval I can define a loop. So for a to a plus h, I'll get the integration, and then if I go to 2, if I go from I is equals to 1 to I is equals to 2, I'll get the integration from a plus h to a plus 2h. So from like from first interval to nth interval, I am calculating all the integral values, and then I'll sum it up. So if I sum it up, that is what the numerical integration which I'll get, the value of numerical integration which I get. And then we can get the value of true value, which we have already seen. And if I do the, if I subtract it and get the absolute value, I'll get the error. So this is the, this is like, if I define the, like if I'm calculating the values from, for all the intervals from first interval to second and third and all these things. Instead of this, we can also like use this formula, which is like directly using the formula also we can do it. So it is nothing but this formula. So this is the formula h by 2 into f1 plus 2 into f2 plus all this f2 plus f3 up to f yeah, plus fn plus 1. So we can use this. So we can use this formula, we'll get the same result. So by using the for loop or also by using the uh, this direct formula, we can get the same result. Like now, if I run it, you can see that earlier when we are using the trapezoidal rule for a single step, which is h is equals to b minus a. We saw that our error was 0.84 something. Now it has reduced. Like now you can see it is getting closer to the true value. True value here is uh, 0.8863. Like it's almost same as the exact value. So that's what this increasing the step size, like that's what we can do by using this multiple step integration. Like so, this will give me an error. So order of the error also is important here. Like if I use the trapezoidal rule, in trapezoidal rule, if I uh, decrease my step size by a factor of 10. Let's say if I have step size of 10, then I'm reducing my step size by zero point 0.1. Then my error will get reduced by 10 to the power of minus 3. So let's say uh, uh, if I do the trapezoidal rule, but what I'm doing is here I am taking the multi-step trapezoidal rule. So in multiple, like let's say if you are taking uh, uh, let's say five intervals initially, like between a to b, if you are taking 5 intervals, and now if you are taking let's say 50 intervals, then your step size basically is increased by a step size gets reduced by a factor of 10. So then your error will get reduced by a factor of 2. So that's what like local integration, local truncation error and the global truncation error, how it varies when we use this trapezoidal rule for a single step or multi-step trapezoidal application. So similarly for Simpsons and 3 also we can. So then we have also seen like these are the simple things which we can see. Uh, in MATLAB, we have default functions which we can use for doing the numerical integrations. So this is the function trapz. Here you can take the value of x and also the fval value. So x you have to define whatever the points which you are taking. Like here, like a and b you have to define, and the f value of the functions at a, a and b, which is f of a and f of b, you have to define. And if you give trapz, it will give you the value of the a of trapezoid, which it calculates. Then we have also this quadrature formula. So actually, this is a number. This is a different kind of integration technique, which is the uh, cross quadrature technique to do the numerical integration. I think maybe in the computational techniques it might have been discussed, but I don't know if it is discussed. You might check if you want to learn about it. So Gauss quadrature is another numerical integration techniques which is used. So this formula basically does that. So here you have to define the function like this, and then you have to give the value of x like between whatever the values which you want to integrate, like a and b. If you give it, MATLAB will give you directly the value of numerical integration between those two values for this function. So the same thing which we have. So these are the things which we have discussed in the uh, module 6. So we have seen the uh, numerical integration techniques, trapezoidal rule, Simpson's one-third rule, and there is also Simpson's 3/8. Like if you want to practice, you can code. It's simply just putting the formula. There is there is not a very that's not a very big deal to just change the formula and check. And then we have also uh, seen this using the functions like MATLAB inbuilt functions, which is the trapz and also quad formula, quad functions, inbuilt functions to do the numerical integration. And then we have also seen the numerical differentiation techniques. So we have seen the forward difference, the central difference, and the backward difference. And we have also seen this for higher order derivative, the central difference formula. And then we have also seen the numerical differentiation for multiple variables, which is x1 and x2. Then we have to go for partial differentiation. So that was all discussed in this module. So do you have any particular doubts in this module? If you have any doubts, you can ask me. Doubts? Okay. 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 So now what we'll do is we'll see this uh, practice assignment. Yes. So this is the first problem, and here we are doing this uh, just just that what the new file edit problem one. So I'll just take this. Copy this where it is there, and I'll paste it. So instead of this, we have x square expx. So x square to exps. So this is the function which we have, and we have to integrate it using the trapezoidal rule and also system. So the lower limit and the upper limit of integrations are 0 and 1. So it's given 0 and 1. And the true value is also given, which is the e power man x e 1 minus 2. So this is the true value which is given already. Now we have to do this. Uh, we have to use the uh, single integration trapezoidal rule, and we have to find out the value of this one. So now in my function file, which we had written for this, we will change this. This is x square into exp of x. And everything else is same. So if I do this, and also I have to calculate uh, what? So first let's see. We'll do this first one and the fourth one. So we'll tackle this later. First, fourth, and the fifth. We'll see this. So this is a problem, and this is a function. And if we do it, we evaluate everything is like safe here, like the same formula we are using, just the function changes. So if I run it, I'll get this values. So the trapezoidal rule formula is 0.64 0.86, right? Single. And for the Simpson's rule, 0.5, this is already like in Simpson's rule, because we take 3 points, step size reduces by half. So we know H is equal to 0.5. So single application of Simpson's. Here the value is 0.009. So this is not the value of the integral. This is the value of the error. If I, this is 0.7278. And the error is 0.009. And here, if I use the multiple step uh, problem, the same thing. I'm just saying they are saying to use two steps. So in this only I'll modify. So this is 0 to 1, and instead of 100, 200 intervals, I'm taking two intervals, and everything is same. Yeah. If I do it, see what okay. Here I have to take care of this. So the x is a vector, dimensions. Thing is, eh, get together. So this is the value. Integration is 0.57, and the error here is 0.165. Let's see if I get. I've done the assignment of this. These are not the things which I should do, but yeah, done it. So that is how we solve the first problem in the assignment. So in the practice assignment, which I intended to do, unfortunately, I solved the assignment 6 problem. Here, the same thing I'll do. I'll change this function in this function. Uh, Differentiation. Okay. Where is the differentiation? Yeah. So in the differentiation, we have taken there is so here I have to replace this values of f. So So like this is a very tiring process. So very lengthy code which we have written. Instead of that, what we can do is we can define a function like this. I think in the assignment 3 or 4 we have already defined the function. It is that yeah. Instead of that, I drop one and then we can give this value. Function is 1y/x minus 10. I am using this dot slash because if I have multiple values which I want to run, then I have do the element wise multiplication or division. Here it is log 6 plus 25, 25 dot slash. So this is the value and the true value here is minus 1 by a square into 1 plus 21.75 by 6 plus 25 by yeah, is a here. 25 by 6, 25 by that's 20. Yeah, this is the true value, and I have to find out first the x value. I have to evaluate at 0.5, and value of h is zero point 0.1. Sorry, 0.001. Let's say I'll just comment this. I'll take h is equal to 0.01. And we don't want all this. We only want the central difference. Central difference. Uh, we'll remove all these things. And I have defined my function, which is where is it? Yeah, we'll save it. My problem, and I'll call this my problem, and I'll give the value of a plus h, and I'll give the value of my problem a minus. I don't want all this for now. Common. Let's see what we are going to get. I want the errors. Something is missing. 914. Output argument are. Sorry. The function, and we have not. So this is the value of a function which and integration differentiation which I'm getting. Let's see how accurate it is. I don't know. This is wrong. It's too different. Now we have got decent value. The point given 5, 0.0274. And now I want to do it for multiple step sizes, which is 10 to the power of minus 3 to 10 to the power of minus 8. Now I'll see what at where I am getting the error is minimum. On here we can see that error is minimum at this point, and then after it is increasing again. So 1, 2, 3, 4. So this is the minimum error. Yeah, 1, 2, 3, 1, 2, 3, 4. For the fourth, so 10 to the power of minus 3, 10 to the power of minus 12, 10 to the power of minus 5, 10 to the power of 6. So at this point, I get the minimum. So now if I check my answers, yeah, these are the correct answers. Something with the error, yeah, 0.39. So if I take this value again, yeah, 0.27. 27498. So all the answers are correct. So this is how we can define a function and then call it here and get use the central difference formula and evaluate the value of differentiation at multiple steps are also like a single step, like whatever is asked. And you can also determine where is the error at what step size the error is minimum, and after that it increases. Like if you go beyond 10 to the power of minus 6, 10 to the power of minus 7, and 10 to the power of minus 7, 10 to the power of minus 8, again the error is increased. So this is the minimum step size which you should take, and this is the minimum error. So that's how we can do. So this this was the first problem, and then we'll see this how we can use the Simpson's uh, one third rule to solve this problem, which is asked. Edit problem. So here I'll put these functions x square plus 1 into, let's say I'll put dot also if I have a vector in case square plus 1 into ext of x. Now I want to calculate the numerical integration and just copy this whatever which we have written earlier, and I'll paste it. Let's see. Uh, Here the integration is from 0 to 1, and the true value is 2 e power minus 2, 2 into e, 2 into ext1, you can see, minus e power 1 basically. So we want only the one third rule. So I'll just comment this, control R if I use, things will get commented. If I use the one third rule, let's see what we just get without displaying it. So by using the Simpson's one third rule, we are getting the value of integration is 2.4467, and the absolute value of error is 0.010. And then he is saying use the uh, step size is equals to 0.05 and do uh, Simpson's one third. So for that, we have to use the multiple steps. So we have to use multiple steps for uh, not even for this, but not even for trapezoid only, but for the Simpson step. So let's just copy this. So there is also a formula which you can use, but yes, I won't use the formula. Just copy this and this will be. H is equals to 0. So we don't know what is n here. So n I can determine by using the value of h. H is something which we know. So N is equals to P minus A by so H they have already given, which is 0.05. And the formula for Simpson's one-third rule is this. That is it. H by 3 into f of A, 4 into f of x plus h plus f of y plus. This is the formula for Simpson's one-third rule. Let's see how it will be. So this we had already done. So I'll just comment it and I'll run this. There is again some error. Ah, yeah. Yes. Dot. Again, we forgot. Is the value of n 20. We can go only till n minus 1. Instance. Everything is good. Let's check what we got. Yes, yeah. Sorry. This has to be into 2. Now let's check. Is equals to b minus a by 2. By 1 h by uh, 2h. Okay. It should come here. Now we are getting a reasonable value. Let's take 1.47, 0.960. There is some error with this. Don't know what is the error. P minus A by 2 divided by N. Uh, some error is coming. I'm unable to figure it out. I think N value should be wrong here. Hmm. N value. Then it's done. Then what is the problem? What is that? Plus H. Thing is right. There is something which is wrong. I don't know what is it. I think 0.05 integration power square plus 1 to power So, um, I plus check. Check. Now let's get okay, 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 okay. Now we have 0.403, 436, and 1.006. 2 minus six. Yeah. So when we go for multi-step Simpson's rule, I have done the mistake. Like instead of going from one to n, we have go we have to go from one to 2n minus one. So we'll have n divisions. So there is it. So like this is one division. This complete three parts is one division. Like that, we'll have uh, n divisions, each having three parts. So that's why we have to go from 1 to 2n minus 1. So that was a mistake which I was doing. Now it's so that's how we can go about doing this multi-step Simpson's rule, and we can get the answer. So the other things like this you can simply get using the trapezoidal functions and quad functions. Simple things. And this is also not like this, just the function values are given, like you can do it. So these are the assignment problems, practice assignment, some assignment problems in the module 6. Uh, this error has taken some time in this session. Sorry, uh, I could not find out for a long time, but yeah, finally it's rectified right now. So, do you have any questions? I'm just low on energy today because like, I was fasting and then I had to take this class. So that's why these things are errors and all. Any questions in this module? Nasir and Anjali, out of this, uh, what will be the pattern of the exam? You mean the final exam, the end exam, right? I think you will get questions like this only. I don't know if you will get coding questions because I like I don't know how you will get access to code in the exam. I think you will get some questions like they will give a few lines of code, and in that you have to uh, tell what is the line which is missing. Like that, you can get a question like 1 mark, 2 mark question, and also like they can give you some code and they can tell you yeah, like simple questions only you get like even if you get coding also like coding won't be like this much big codes you won't have to write. They might give you some 1 or 2 lines of code which is missing, and they will tell you what is the line of code which is missing to get some value. Like that you can get a question, and they can give you some code, and they can ask you what will be the output of this code. Like that, I think those sort of questions will be there. I don't think you can get some access. Yeah, multiple choice. It will be multiple choice, and also these things also will be there. Numerical answer type. You have to fill something like obviously like like if there is no coding and exam, like if they don't give any coding environment, like I don't think they will be able to give you any coding environment. So there will be simple questions for this, like for which you can calculate some value. Like they might give you some code and you can tell like what is the output. This is the output, something which you'll get like that. So then you have to write. Then you have to enter this value. So like then based on that you will get like if your value lies between this range minus 19.5 to minus 19.1, then you will get the marks. So This multiple choice also will be there, and also these kind of questions will also be there. Uh, numerically, numerical type answers, numerical type questions, both will be there. I'll find out. I don't know if coding will be there in the exam. I don't think it will be there. If they, the I'll find out from the course coordinators. Uh, Probably I'll tell you in the more clarity, more clarity on that. Okay. Any other doubts? Okay. 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 I think we'll stop today. I'm very tired. Okay. Sorry. I'll just, uh, if you have any doubts, you can always email me. Uh, this is my email ID. I'll surely try to help, like in whatever way I can. I'll surely try to help you. Like not only in this, like if you have any other doubts regarding something else also, like in your academic something else, you think I can help, I'll surely try. Okay. Okay. Chalo. Thank you. Thank you for joining. Thank you guys. Yes.